Hi, and welcome everybody. Hi, Stefan.
Hi, Rainer. Hi, everybody.
How are you, Stefan?
I'm doing good. I'm very excited about today. And I have a free evening again. So I took my entire family to my parents. So
Oh,
I'm
really?
free for the evening.
Ah,
Um, so
nice,
yeah, looking forward.
nice. Yeah, I think it will be a great evening. The sun is shining outside. I had to take the blinds down because it's such a beautiful evening. Best conditions for Rust meetup, right?
Absolutely.
Perfect. Let me share my screen so we can do the community news. And here we are. Nice. So let's go through the community news. As always, after the welcome, we will inform you about what's coming up today and, of course, what's generally happening in the IT community here in Linz. We have put together some hopefully interesting news for you. First, as you might already know, if you have been to the Rust Linz meetup multiple times, this is brought to you by the Coding Club Linz. We are a volunteer-driven coding club where people come together who are passionate about software and IT in general. Now, today we have two awesome speakers. Stefan, do you want to tell us a little bit about the two upcoming talks of today?
Yeah, sure. I'm very happy that we have those two talks because I have been engaged with both of them in the past. First is Deepu Sasitharan. I hope I pronounced it correct. He smiles, so yeah. Who is now a developer advocate at Okta and the co-lead of GHipsy is also a Java champion as of recent. As I've heard, and I really enjoyed that I can finally invite Deepu to one of my events because back pre-pandemic, I was supposed to give a 3-hour TypeScript workshop at DevOps in Belgium, but at a very, very last minute, I had to cancel due to some family emergency. I wasn't able to attend. And Deepu took my proposal and did everything on his own, just like that. So he really saved my ass in that situation. And I'm internally thankful for that. And I also watched the video. It was a fantastic workshop. And ever since I was following him and looking at what he was doing. And just recently started experimenting in Rust and Rust and Kubernetes, which are two topics that are very close to what I'm working with. So I'm really looking forward to what he has to present. And the next one is Nick Cameron, who does Rust at Microsoft, but there's a lot more to that. I guess he did basically everything in the past. So he was part of the language team, part of the compiler team, part of the tooling, part of IDE support. So back when the Rust teams were, I guess, evolving, I don't know, he did basically everything. So, but this is just something that I found out after I got in contact with him after Daniel Stenberg's talk that we had a couple of months ago about curl and Rust. And it was a conversation on Twitter. And coincidentally, at the same time, I also watched a video from him about design patterns. So I said, okay, somebody who I'm in contact with, just at the moment, I watched the video. Let's ask him if he wants to speak at Rust Linz, and he agreed. So I'm very happy for that. And thankfully, he's talking about a topic that's also very close to me, which is async Rust. So, hey, this is going to be my show. I invited lots of speakers just for me. No, just kidding. It's, of course, for all of you too.
That's the advantage of organizing a meetup, right?
Absolutely. So yeah, this is now working time. I book working time because I'm educating myself,
Very good, very good. We are so thankful to have Deepu and Nick today at our meetup. So let's quickly go through the community news so that we can start with the first talk. Is that okay for you, Stefan?
Let's go.
Very good. So here we are. If you want to join our Discord server, you can do so. Discord server is great. If you want to ask questions, you can send them there. You can also use the YouTube chat just as you prefer. But Discord has the advantage that we can do some additional discussion maybe after the talk. So everybody is invited to our Discord server. And I think Stefan will post the URL. Yes, he already did on the chat, so you can copy it from there. Now, to the community news. For those of you who are regular visitors of the Rust Linz meetup, you know some of the events. Again, Coder Dojo Linz, the programming club for kids, as every week. We have tomorrow 4 online workshops for kids between 8 and 17. We cover a lot of topics, and tomorrow we will have Scratch. We will have some server-side web development. Stefan, just for you, TypeScript, lots of TypeScript. We will have some client-side game development, simple browser games for juniors, and we will have a soldering electronics workshop also taking place tomorrow. Everything is free, everything is virtual. So if you know young coders, people who are passionate about young people who are passionate about learning, about software development and electronics, tell them about the Coder Dojo Linz tomorrow afternoon. Female coders, our friends in Linz, they do their next study group on the 4th of May. So if you consider yourself female, or if you are a girl, for instance, and you want to get into technology and you are looking for a community of other female coders, that is exactly the right community for you. 4th of May. Now, this one is important for me personally because, I'm a little bit of the main organizer of this thing. It's the Global Azure event, which will take place next week on Friday, tomorrow in 1 week. It's the Global Azure Austria event. It's a community event from the community for the community. It's 100% free. We have 4 tracks, a full day packed with a lot of content about cloud computing and also related development technology. And it happens that Stefan will give a Rust talk there. Stefan, we will hear about serverless Rust on Azure, a deep dive. So if you want to know more about that, feel free to register for the Global Azure. You can watch one talk, maybe the one from Stefan, or a lot of talks, just as you like. As I said, it's a community event made possible by a lot of awesome sponsors, and it's 100% free. Next one, the cloud native computing in Linz, the meetup will happen, the next one, on May 31st. I've heard that they have not announced this date yet on their website, but we already got this news directly from the organizers, so you can now save the date. May 31st will be the next cloud native computing workshop. The speakers haven't been set yet, but watch their website. It's listed here to get more information about their meetup. Now, an additional event. This is not a community event. It's a commercial event. It's the Rust Summit. Stefan and I had the possibility to help a little bit in setting up this Rust Summit. It will take place mid-May. You see the date on the screen. And the nice thing, why we mentioned that here, is that the organizers really care about offering this summit to the diverse set of people. The diversity topic is very high on their agenda, and they gave us the possibility to give out diversity tickets. So maybe if you are a student and you don't have a company paying for your ticket, or if you are a member of an underrepresented group in the IT technology, don't hesitate and send us an email. We can make sure that you get a diversity ticket. We have a limited number available, but if you want to have one, it's absolutely no problem. Don't hesitate. Shoot us an email. Here is the email, the info email from it's called Coder Dojo from our programming club, but it comes to me, and I will definitely make personally sure that your request is handled accordingly. We want to thank our sponsor for today's meetup. Our sponsor today is Microsoft. They are helping us making this meetup possible. Although it's a virtual meetup, we have some costs, and without sponsors, it would be pretty hard to set up a meetup like that. And we want to say thank you. And of course, we offer Microsoft the possibility to tell us a little bit about them. And here you see the slide that I got from them. Microsoft asked me to point out that they have a lot of awesome learning resources on Rust, and especially Rust and Kubernetes. And here you see the QR code and the short link. So if you are interested in that, please follow the QR code or the link. Also, they asked me to mention the MS Staff AT Twitter account. It's the Austrian Twitter account for Microsoft developers. So if you don't follow this account already, You are invited to do so. And yeah, this was our sponsor news. And Stefan, I think with that, we are through. So let me get this one up. And I think we are ready for the first talk.
I think so too. So yeah.
Let's ask Deepu on the stage.
Hey. Hi, Deepu.
Deepu, you are still muted.
Oops, sorry. Yeah, thanks for the nice introduction. Man, that always gets me.
Cool.
Deepu, where do you broadcast from? I always ask our guests this question because I'm so interested in how global or local we are. Where are you based?
So right now I'm in Utrecht at my home in the Netherlands. So that's where I'm broadcasting from. Last week I was in India still, so I would have broadcasted from there. So just came back. So
very good. And today you are in Austria, here in Linz, broadcasting for the Rust Meetup Linz. Have you ever visited Austria before?
Not actually. No, not yet. Austria is still on my list. So.
Awesome. So we would love to have you as a visitor at some time in the future. Let's see
Definitely.
if we can make that possible in the future. Deepu, are you ready for your presentation? Can we get things going?
Yeah, sure.
Awesome. Very good. So the stage is yours. Did you already share your screen? I think you did, right?
Yes.
Okay. We see your presentation. Deepu, thank you again for being with us today. And we are looking
thank you
forward
for having me.
to the talk.
Thank you. Awesome. So let's get started. As you all probably already know, so today I'm going to talk about some Rust in the Kubernetes space, right? I do want to give out a disclaimer. I'm not a Rust expert because I see Nick, coming up after me, who is probably a Rust expert. I'm more of an intermediate Rust person. So keep that in mind. Cool. So small introduction. Of course, Stephen gave me a good introduction, but just so that I go through my regular script. So my name is Deepu K. Shashidharan. I'm the co-lead of JHipster. It's a nifty code generation platform or rapid application development platform, the Java world. I'm also a Java champion, quite recent, so it's also a bit weird that I'm here talking about Rust, but that's all fine. I also created a nifty dashboard called K-Dash for Kubernetes, among many other open source stuff. I'm an open source aficionado. I have been doing open source for, I think, 7-8 years now. I'm also a polyglot developer. I work on Java, JavaScript, TypeScript, Go, Rust, among others. So I don't discriminate between languages, not much. So I work at Okta as a developer advocate with a focus on DevOps. I also frequently write on my personal blog about tech topics. So you can find it on deepu.tech if you're interested in my content. You can also follow me on Twitter if you want to get updates on content I publish. I have also written some books, mostly around JHipster. And you can find most of my social handles on the screen. So let's get started. So before we go into the topics of how Rust fits into DevOps world and how it is better than Go and all those things, I want you to introduce you to something I built. So it's called K-Dash. So it's a simple terminal dashboard for Kubernetes. It provides common resource views, node metrics, logs, and so on. I can give you a quick demo. So this is it's a CLI dashboard. Basically, reads out from your Kubernetes configuration, and it shows you a kubectl kind of view, but more interactive. So there is full keyboard navigation, where you can go through stuff. You can switch between contexts. You have a really nice utilization view that shows utilization for your entire cluster, which is quite handy in my opinion. You can also do basic stuff like switch between your namespaces, see basic memory CPU usage on the screen. There are more stuff like log streaming, for example. If I go to if I go to pods, I can go into the pod. I can stream the logs from there, for example. Of course, you can get your describe or describe as YAML and all those things. So yeah, that's about it. So that's the tool. So let's get back to the So the utilization metrics is something that you probably won't find in many other tools. So that's like a highlight feature that is built into Kdash. I wanted to show you that so that I can ask this question and I can set some context, right? So I built Kdash, the CLI tool Kdash, and was my first serious Rust project. So I have been, going through Rust stuff, learning here and there a bit of Rust, trying, small things. I never had an opportunity to build something holistic, So I was pondering over what to build, and I finalized on building Kdash, and I built it in Rust, and I learned a lot of Rust while building Kdash. I have to say it was a really fun experience. I never had so much fun in the recent few years working on anything as much as I did on Kdash, and I think most of the credit goes to Rust being an awesome language, and the developer experience of working with Rust being so awesome that I was like addicted to working on that. I would wake up early mornings sometimes with some idea on my head, and I'll start coding. So that is how interested I was in building that using Rust. And I have, in my career of like 12 years or something now, I had never been that excited except from the earlier years of my career in coding and building something. So that was a really fun experience, and all credit goes to Rust, as I mentioned, right? So the question would be, so why did I build another Kubernetes dashboard, right? Because there are so many solutions already out there. I mean, kubectl itself is already quite good, though it is not interactive. It's already quite good enough. And there is also the K9S project, which is built in Go, but it's very similar to Kdash, and of course, it offers way more than Kdash. Like it offers CRUD actions on your K8 resources, whereas Kdash is mostly view only, right? I don't think it's quite obvious, right, that Kdash is inspired by K9S, because a lot of features are very similar. The UI is slightly similarish, though I try to make it a bit more user friendly and a bit more easy to navigate and everything. But it's heavily inspired by K9S. So when I started learning Rust, I wanted something, build something which is more than hello worlds and to-do apps. And I wanted something serious, something that has a good architecture, something which will have a lot of challenges. So I decided to also build something that could be useful, right? So and since I'm on the Kubernetes space a lot, I thought it would be nice to build something in the Kubernetes space, so that I can also kind of POC the idea about using Rust for Kubernetes tools. So I was also using K9S, and there were some things that was some things I preferred to be better, and in terms of user experience, in terms of speed and stuff. So I thought it could be a nice idea to build something similar, since there weren't many other projects similar, especially there was nothing in the Rust space. So I decided to go ahead with that. The focus when I was building Kdash was definitely UX and navigation. That was the primary goal. Of course, the speed and everything just was add-on provided by Rust, right? So that was not the focus. So simpler user experience and navigation was the focus. But of course, in the end, when I finished, without doing anything or without spending any effort, I did also get a way better efficiency. Like Kdash uses much less resources than kubectl. Of course, then much less resources than K9S, but also then kubectl. Even if you're running kubectl commands on watch, it will still use way more resources than Kdash. Of course, it's not like too meaningful when we talk about in megabytes, but still it uses way more resources than Kdash. So that's all from Rust, for free. And the obvious question I get after when I talk about this, the obvious question I always get is why Rust and why not Golang? Because most of the stuff in the Kubernetes world is built using Go, right? And even Kubernetes itself is built on Go. And most of the tooling, the infrastructure around Kubernetes is all built in Go. So, and it has, Go has a lot of libraries to help build Kubernetes ecosystem tools and stuff. So why not Go? Why Rust? What advantages do you get, right? That's a valid question. And since most of the Kubernetes space is built with Go, honestly, Go is an excellent language for these purposes, right? And there is not a lot of solid reasons to choose Rust over Go for a user space project like K-Dash. That's a different thing. But there are Kubernetes use cases where Rust is a way better choice than Go. Some ideal examples would be sidecar applications like a proxy, similar to Linkerd or Envoy. Linkerd proxy is already written in Rust. So proxies, sidecars are like applications that would live alongside your pod, in your cluster, and they have to be lightweight, they have to be fast, they cannot have a lot of overhead, so that they don't slow down your actual applications. So sidecars are ideal use cases where Rust would make a lot more sense than building in Go, for example. These days, sidecar applications mostly are either built in Rust or in C++, because efficiency and speed is the huge importance. So Rust would be ideal for these kind of projects. In-cluster tools like log aggregation, monitoring, eBPF, building Kubernetes operators, WebAssembly workloads. These are also use cases where Rust would be a much better choice than Go when it comes to building the Kubernetes ecosystem, right? But for user space projects like K-Dash, for example, it doesn't make that much of a difference. You can build it in Go or Rust. In the end, more or less, there won't be a huge difference. Of course, the Rust version might be more efficient in terms of resource usage. It might be a bit more faster, but for user space projects like a CLI, I don't think it matters that much. And the real reason I chose Rust for K-Dash was, of course, to evaluate Rust as a evaluate Rust in these kind of use cases, and also I wanted to build something a bit more complex in Rust to see how it works, to get the ins and outs and stuff like that. So overall, I do believe that Rust is an ideal candidate to build out the Kubernetes ecosystem, along with Go, of course, because Go still has value, and adding Rust into the mix would only make the ecosystem better. We would have a lot more, much more safer applications, faster applications, and so on. There is already a lot of things coming up in that space. We'll talk about that in a while. In my opinion, when we talked about the ideal use cases, right, and even for user space, if we have to nitpick, then definitely there are a lot of advantages that Rust offers, right? Again, I'm not going to go into details because I believe most of the people tuning in are familiar with Rust and they know what Rust is and everything. So I'm just going to go to a few things that I consider quite important. Of course, safety would be the number one benefit, right, of using Rust over Go. So memory safety is currently like one of the biggest issues that we have, right? Memory safety related issues are like cause of majority of security CVEs we encounter. Undefined behavior can be abused by a hacker to take control of a program or to leak privileged information, right? In memory safe languages, if you try to access an array element out of its bound, you'll just crash the program with a panic or error, which is predictable behavior. Whereas in memory unsafe languages like C++, which we are still using to build, like sidecars and proxies, like Envoy proxy, for example, right, still being used. So there is a lot of chances of introducing security vulnerabilities, right? And these stats kind of, if you put this together, it's like memory safety issues are causing like more than 70% of CVs we encounter across platforms, across products. So why do we still fall for that, and why do we still use memory unsafe languages to build tools like proxies and stuff like that? So in my opinion, Rust can be a boon in that area, especially to build out such what do you call, like sensitive applications, or like such integral applications like proxies, especially for service meshes and so on. So for me, safety is like the number one advantage of Rust over Go. So memory safety, of course, thread safety also causes issues. And I think recently there was thread safety and also type safety. So I think I put this in the wrong slide. This should have been in the thread safety slides. Yeah, so recently the Microsoft team found some issues with Helm, which is written in Go, race condition issues, which would never happen in Rust, right? So these are the safety guarantees that Rust gives us, which would be very helpful for us. So Helm is a user space project. So even for that, Rust still would make it better. Though ideally it may not make it way better, like in terms of proxy or something, but it still would make it better. So the safety thing, and my most favorite thing about Rust, hands down, is like the zero cost abstraction features, right? So I assume most of you already know about this, but just to summarize, so in Rust, one thing I loved when I was working on Rust and when I was writing the project K- in Rust was I didn't have to constantly worry about picking the right approach. For example, I didn't have to worry about, hey, should I do this as in function? Should I follow functional programming approach, or should I do imperative programming? Should I do object oriented? I didn't have to worry about any of this because it didn't matter. In the end, the style of my the style in which I programmed didn't matter, because the zero cost abstractions ensured that regardless of how I wrote my program, the end result was always as performant as it could be, right? Which is not the case in many other languages. Like most other languages, I think except for C++, I think no other language offers zero cost abstractions like this in this way. So I think that was quite freeing in my experience. It took away a lot of the thinking process that you would normally have to do. So I didn't have to worry about that. I could just have fun in coding. Like I could go like ahead and like do whatever I want. Of course, like not talking about doing bad programming practices, but at least I could go like go ahead and do full-fledged functional programming without having to worry about any any performance impact. Or I could create layers and layers of abstractions, and I didn't have to worry about these creating performance impact. So that was like one of the greatest thing that I experienced and I liked about Rust, which I think is way undervalued feature, I would say. For example, right, like, so I'm a long-term Java programmer as well. So you can see on the left is a Java program, on the right is a Rust program. Both are doing quite similar stuff, right? So it's doing factorial using three approaches. So there's a factorial using traditional for loops, like the imperative way. There is a recursive way, and there is factorial using the inbuilt functional APIs. So in case of Java, it's the stream API, and for Rust, it's the inbuilt functional APIs like fold in this particular case. And if you look at the benchmark, so I ran benchmarks for both. For the Java benchmark, you can see the factorial with loops performs the best. It's very obvious, right? Because imperative code, in most of the cases, imperative code will have better performance because there are less indirections and there are less abstractions, right? And then the recursive one was twice, like twice as worst, if that's the right way to put it. And then finally, the inbuilt functional approach was like a slightly bit more slower. So of course, that's expected. This is expected in language like Java or language like Go. Most languages, especially high level languages, which does its own memory management and whatever. So this is to be expected. Whereas in the Rust version, the performance for the loop and recursive versions were almost identical, and the performance for the inbuilt performance using the inbuilt functional abstractions was even higher. And I looked into, I was surprised at first. Then I did some digging around and I found that, okay, the inbuilt, a lot of the inbuilt abstractions also have additional, bound checks and these things that improves performance. Of course, in my naive, sample implementations, I didn't do any of those. That's why there is additional performance. But the takeaway is that because of zero cost abstraction, the style is not going to matter. So you can go full functional, you can write imperative, object oriented, whatever. It doesn't matter. It's going to give you the same performance once it's compiled, and you don't have to worry about it. So that's like the one of the best features of Rust in my opinion. So of course, there are a lot more other things that I like about Rust. For example, the tooling and community is one of the best that I have encountered. Like, I have worked with many languages, and so far, I don't think I have come across any other language which has such nice compiler, such user-friendly tooling like Cargo and the entire ecosystem, and also the community, such helpful and vibrant community. So that's definitely another plus point for us. The tooling is way better than Go in my experience. I have done some serious development using Go back in the days, and huge projects with like a medium-sized team, and the developer experience of using Go doesn't even come close to the developer experience of using Rust. So that's also another plus. I don't want to turn this into a Go versus Rust thingy, so let's move on. So of course, high-level languages versus lower-level languages. I think you all know the difference. Rust kind of sits in the middle, right? Because most high-level languages will give you a choice between safety, speed, and abstractions. You can only choose two. So if you take C++, you can get speed and abstractions, but not safety. If you take Java, you can take safety and maybe maybe speed, a little bit of speed, but no abstractions probably. And if you take Go, then it's the same, right? So that trade-off is not present with Rust, because you get safety, speed, and abstractions. You get all three, and you don't have to choose. So that's where I think Rust stands out among other languages. So also, again, this research has some controversies around it, but a 2017 research which compared speed, memory efficiency, and energy efficiency of programming languages put Rust in the top 5. So in terms of course, speed and time, Rust was like a second, right behind C, which makes sense. Because the speed would directly correlate to energy. Of course, it didn't fare that well in the memory usage, which was contested, because in real world experiences, even in my personal experience, the memory usage of Rust was anecdotal evidence, of course, but I didn't have a case where Rust was using more memory than Go, for example, right? So this could be based on the implementations they chose, and of course there was I think there was some difference of opinion in the community about how the implementations were done, but it's still good to know that Rust is quite energy efficient, which makes sense because it's quite fast. So in my opinion, people won't appreciate Rust unless they spend few weeks building something in it. So the initial steep learning curve is there. It's a thing. So it could be frustrating or challenging depending on how you see it. For me, it was challenging, but I can also see that it could be frustrating for someone if they are just trying to get something done, right? But once past that point, maybe a few weeks in, I think it's hard not to love Rust, right? It's like a toddler with superpower, right? And honestly, writing Rust code is much more pleasant experience overall, like compared to many other languages. So I really like this quote from Tech Republic, which I think is really is quite true, I would say. So let's get into some use cases and the ecosystem that we have in terms of using Rust with Kubernetes, right? So we spoke about WebAssembly. I didn't want to go into too much details of WebAssembly because I believe there was some talks around WebAssembly and Rust in the past. in the meetup, so I don't want to go too deep. But the WebAssembly System Interface, or WASI, makes it possible to run WASM workloads in Kubernetes. And it's still quite new and has a lot of rough edges. I wrote a blog post about it. You can find the link on the bottom of the slide. It's quite rough. It's not definitely not production ready, but it could be the future of a containerless Kubernetes, because WebAssembly would make Docker containers obsolete, because they both do the same thing, but WebAssembly containers or WebAssembly OCI images, you cannot call them containers. Like WebAssembly, right? It's its own format. So WebAssembly gives the same advantages as containers, but gives more sandboxing, more security, and stuff like that. So it's like a better alternative to containers. So if this technology gets adopted, gets a good ecosystem around, there are still some issues like networking is a mess currently, so those needs to be taken care of. So once all that happens, I think WebAssembly on Kubernetes has a bright future and can make containers obsolete. Of course, not talking about like in the short term, but in the long term, because migrating from the current world of Docker is not going to happen overnight, right? So that's going to take some time. But when we talk about WebAssembly and WASM workloads in Kubernetes, of course, you can build WebAssembly WASM binaries using any supported language. You don't have to do it in Rust. But Rust has one of the best tooling and ecosystem for WASM. So and that makes it an ideal language to build WASI workloads for Kubernetes as well. So by that argument, because it has one of the best developer experience for doing WebAssembly, and has like a lot of libraries, tools, and stuff. And another reason is a lot of the current infrastructure around WASI or WebAssembly on Kubernetes especially is built using Rust as well. So that is going to spill over in terms of tools, libraries, and stuff like that. So that's going to also make it a nicer experience to work with Rust, in my opinion. So for example, WASM time is a JIT style standalone runtime. This is what makes it possible to run WebAssembly on Kubernetes, for example, because WebAssembly was originally meant for the web. It was meant for web, and it was meant to run in browsers. So in order to run it outside of a browser, you need a runtime, and WASM time is one of that runtime, which is open source. It is written in Rust. It's still kind of not production ready, I would say, but it's a runtime that is being used by many other projects at this moment. There is also a few other runtimes. There is WASM Edge, which is runtime focused on microservices. It's more commercial oriented. It's focused on microservices. It is built using C++, but also offers Rust binding, so that you can directly build against that, like applications against that in Rust. So and there is WASM Cloud, which is focused on distributed actors rather than workloads. It is also written in Rust. So all these three runtimes will let you work with Rust, and it makes they all provide Rust bindings. I mean, two of them are written in Rust. That means you can directly use them in your Rust project. WASM Edge provides Rust bindings, so you can also use that in your Rust project. So it makes it easy to build stuff for these runtimes. And finally, there is also Crustlet, which is based on WASM time. It's a kubelet written in Rust and can run OCI, so WASM binaries in the OCI format. So WASM binaries can be built as OCI images, open container images, though they are not containers, but you can still build them as OCI images, and you can run them using Crustlet. And the blog that I have linked down here, it explores that particular use case using Crustlet to run Rust WASI binaries, right? So WebAssembly is one area that I'm looking forward to, especially in terms of seeing more of Rust here. And that's one area that I'm keeping my eye out from a Kubernetes plus Rust enthusiast point of view. So the next use case would be in cluster tools, right? Proxy, sidecar, service mesh. We briefly spoke about this. Of course, Rust is going to make it much nicer in terms of course, it's going to be fast. There's going to be better safety than using C++. It's going to be efficient, right? And so it makes it ideal for building sidecars, proxies, service mesh infrastructure, stuff like that. So Linkerd is already a very popular proxy. So I think Linkerd and Envoy are the two most popular proxies in the Kubernetes world. And Envoy is written in C++ and Linkerd is written in Rust. So Linkerd was originally written in Go, which was later migrated to Rust, which makes sense. Then another use case would be K8 as operators, right? So Rust asynchronous programming model is a perfect match for building high performance or high throughput or highly parallel operators. So you can have operators which are doing parallel processing without having to worry about race conditions and stuff. You can build high performance operators. So this is another use case area where Rust would shine better than Go in terms of performance and in terms of ease of use. It's going to be light on resource usage and footprint, and also it's going to be way less code to write. Writing an operator in Rust and Go is going to be different experience, because with Rust you can, once you have some basic so macros or something, then building out new operators would be like quite straightforward and very little code compared to how you do it in Go, for example. Another use case would be log aggregation, monitoring, eBPF, and these kind of things. So especially in a Kubernetes container where you want your resource usages to be kept minimum so that your applications can have more resources, it makes sense to build crawlers or log aggregation agents and these kind of things in Rust, so that they take very little footprint. They don't impact too much in terms of performance, and they're quite fast as well, right? Another area would be eBPF, which is the current kind of the ideal way to collect logs or for observability, right, in the Linux kernels. So there is already a solution called RedBPF, which is a tool chain to work with eBPF, which could mean that in your Kubernetes setup, you could use this to build, log observability solutions, monitoring solutions, logging solutions, security solutions, and so on. So these are all the use cases that I'm kind of envisioning for Rust in the Kubernetes space. And of course, there is finally user space tools. I won't say this is the most important aspect, because in-cluster tools and WebAssembly would be the most important, and is use cases where Rust can actually add a lot more value than the current solutions out there. In the user space tools, of course, you can build stuff using Rust. It's not going to have too much of an impact compared to building in Go or something, but it's still possible. I mean, I built K- using it. There are a few others which are quite nice. Like there is QB, which is a Kubernetes context switching and prom modification utility for your shell. There is kubectl view allocations, which is a library that I have used in K- as well to see your Kubernetes usage metrics and stuff like that. And then finally, there is Click, which is a command line interactive controller for Kubernetes, more like a REPL for Kubernetes. So these are, and there are a lot of other smaller user space tools, and of course, anything that you can build in Go, you can also technically build in Rust. So for a Rust programmer, it shouldn't stop you from building Kubernetes tools. Just because you don't want to write it in Go doesn't mean that you don't have other options. You can still write it in Rust. And of course, for this, we would need a library ecosystem. There are quite some. I won't say it is as good as Go in terms of the diversity of libraries, but most of the important ones are already there. For example, kubeRS, which is a Kubernetes client for Rust. So I use that in K-. So this is equivalent to the Go Kubernetes Go client in terms of features and everything. It doesn't have some bells and whistles, but since it is written in Rust, we have really nice generics and macros and stuff like that. So the library also provides some generic traits and stuff, which you can easily extend to bridge whatever gap you will find. For example, when I used the kubeRS library, the metrics API didn't have any implementation in this, whereas the Go version has a metric API implementation. And so I was like thinking, I don't have this, so should I use another library? Should I use my own? Should I just build my own bridge between that. But then I went to the QBRS issue list and opened an issue, and then there was a really nice suggestion. Hey, we have this generic trait, just implement this and you're done. And that's it, like 5 lines of code, and I was done. So even to implement a feature that was not there, it only took like 5 lines of code, like using that generic and providing some configuration, and that was done. So it's as easy as that. Of course, QBRS uses K8 as open API underneath, which is the Rust bindings for Kubernetes. Then there is QBRT, which is runtime helpers based on QBRS. There is the R operator, which makes writing Kubernetes operators in Rust very easy, because it provides macros and stuff for that, which you don't have to like it provides most of the boilerplate. Then you have Risotto, which is a Rust SDK for AWS. And of course, there is also the official AWS SDK for Rust. And there is a Prometheus parser to parse and validate Prometheus query expressions. Of course, there are a lot more smaller libraries you would find. Of course, you'll find a lot more libraries. I just listed the ones with a lot of users, or like a lot of downloads and stuff like that. A lot of smaller ones. But the ecosystem around Kubernetes for Rust is still evolving. I won't say it is unusable at this moment. It is still. I have seen a lot of production examples of these libraries being used. So it is as good as I won't say it is as good as the Go ecosystem, but it is getting there. I think in few more years, I think this would be as good as the Go ecosystem. So this would be ideal time to actually start considering Rust for Kubernetes-based use case. How much more time do we have? I think.
Deepu, don't worry about the time. We are perfectly fine. It's
Okay.
6:15, so we are listening carefully to what you tell us.
Okay, no, this was like I had some optional slides. I wanted to make sure if I have time to go through them. So I think I have a few more minutes to go through. So that's fine. So yeah, I did want to touch up a little bit on the K- architecture, just to show it wasn't all hunky dory. So I just wanted to go through a few things I learned on the way. So K-, yeah. So I used a bunch of libraries. So I did want to mention them. So TUIRS was like one of the best UI libraries that I have worked with. It's so nice. So it helped me build a rich UI on the terminal. So that was really good. So it's like what are those, the old I forgot the name for it. What are they? Okay, never mind. Then there is Crossterm, which is a terminal manipulation library, which is used by TURS. TURS supports few other terminal manipulation libraries as well. I went with Crossterm so that I can add support for both Windows, Linux, and Mac. Of course, Tokyo is unavoidable in any Rust project these days, because K- is fully event-driven and non-blocking asynchronous stuff. So Tokyo was like a obvious choice for that. And of course, QBRS with K8 as OpenAPI, OpenSSL, and all those stuff. kubectl view allocations for some metric stuff. Clap for command line argument parser. Used a few other smaller libraries like Rust clipboard, Serde for serialization and stuff, and Ductars. So these are the libraries I used. And data architecture wise, I started out with something simple, like any other person trying to learn Rust. And soon I started getting roadblocks and started learning more and more about asynchronous Rust and stuff like that. And in the end, decided for something like K-, it made sense to make it completely event-driven, so that there was nothing blocking. And since I was using Tokyo, it was quite easy to split everything into multiple threads. So there was like one thread which was just taking care of rendering the UI. There was another thread that was taking care of network requests, and there was another thread that was taking care of parsing commands and like running commands and stuff like that. So I think there are 3 or 4 threads, and there is one data store, and I used Arc plus Mutex for a shared state data store. So that I mean, of course, in Rust, it was so easy to do this, because didn't have to worry about data races and stuff like that. And having Arc Matrix as a single data store with multi-threads and event-driven architecture made it simpler to show the data and like to update the data and stuff like that. I didn't want to go into much more complex data structure for that. The threading is a bit more complex than it is, but again, Rust plus Tokyo made threading so easy that after a while I even forgot that I was working in a multi-threaded application where I had normally, like for example, if I was doing the same in Java, JavaScript or something, or even Go, I would have to be so much. I would have to pay so much more attention into data races and not corrupting data from multiple threads and stuff like that. Here, after a while, didn't even have to worry about it. And honestly, I forgot that I was working in a multi-threaded asynchronous application. And of course, non-blocking UI and stuff like that, thanks to multiple threads and event-driven IO. So the only bottleneck I faced was the network IO with the Kube API server, which is because the API server itself is not working in a non-blocking asynchronous way, right? That is the only bottleneck I still have. So I'm hoping that will improve on the library side, and this part will be better. It's not noticeable, but if you do too many network requests, you can sometimes see the bottleneck. Of course, there were challenges like log streaming was like the most challenging part for me. It was because the way log streaming was provided by the underlying Kubernetes library didn't work with the architecture that I was trying to implement. So because it was blocking, and I had to do a lot of work around. I had to switch around a few Tokyo plugin libraries, so that I can add polling, retries, and these kind of things. But yeah, in the end, a separate thread for streaming and switching to Tokyo streams helped with some of the issues that I was facing. There are still some quirks which I haven't ironed out yet. I'm assuming that as I learn more and as I become better in overall Rust async world, I can fix some of those. The UI was initially blocking before I split it into multiple threads. I had one thread for everything, and the UI was you could notice bottlenecks on the UI because the UI will become unresponsive whenever there is a network call being done and stuff like that. So splitting into multiple threads helped with that. And another issue is that the version update of Kubernetes, because Kubernetes, K8 is open API, and anything that uses these, like any other library that uses these, has to be carefully updated. You cannot have multiple versions of K8 as open API in the same project because of how that library is published. It can only support one Kubernetes version at a time. So if there are multiple libraries in your project using the same libraries, then you will have issues whenever you compile. You would have to play around. You would have to play around and make sure that it works. And even if you do that, again, when some library updates a version, it could break again. So that part is still a bit of a what do you call, like a challenge. I haven't found a proper solution yet. For one of the library that I was using, I worked with the author of the library to to find a solution. We have some sort of workaround solution which works for now, but this could happen for anyone, I would assume. So I think that's it from me. Thank you so much for letting me share my experience and to share my love for Rust. If there are any questions, I'll be happy to answer.
Deepu, thank you so much for this super interesting talk. I listened to everything very closely. And my first question to you is, could you please share your slides with us? There are so many interesting libraries on it, so many links, and I couldn't make note of all of them. So it would be very helpful to have you. You could post them yourself on the Discord server, for instance, or you can send them to us via email, and we can do that for you, just as you prefer. But that would be really great.
Definitely. I'll share the slides immediately after this.
Perfect. Thank you. We have a bunch of questions from the audience. Stefan, I think you already took a look, right?
Yes, so there are a couple of questions. The first one is from Elvin. Hello, Elvin, long-time visitor of Rust Linz. Happy to see you again. And he's asking, what framework did you use for the K-UI?
Sorry?
What framework did you use for the K-UI?
UI, yeah, it is the TUIRS. The first one, let me share my screen again. I think I stopped. The first one I talked about. Let me share it. So this one, TUIRS, it's the UI library. It's awesome. It's a really nice UI library. So easy to use, and like it would be like like with that library, I built this UI in like 2 hours. So like approximately 2 hours. So that was so easy to put together.
It's fantastic. It looks beautiful. So
thank you.
It's pretty amazing.
Nice. all thanks to the library.
I definitely have to check it out. I'm old enough. I grew up with these kinds of UIs, and I always passionate about these things. The next
they're back in fashion.
Absolutely, they are.
I forgot the name for this. There was a Curses, right? Curses UIs. It was used to call Curses, right? Yeah. Okay.
Yeah.
That's the name.
Nice.
Yeah.
Cool.
Here we have one question from Daniel. He asks, you mentioned memory safety as one of the biggest causes for security issues. What percentage of these issues do you think would go away by simply switching to Rust? Daniel is assuming that not all of them will magically go away, but what do you think? What is your best guess here?
Yeah, of course. It's not going to all go away because we still have unsafe Rust, and I'm pretty sure most of the use cases, especially any use case that touches hardware, you would have to do unsafe. There is no way around it, right? If it is touching anything at a low level, hardware level, you have to do unsafe code because that's the way it is, right? So I don't think it will go away, but there is a lot that will go, because if you analyze a lot of these CVEs, right, a lot of them could have been avoided by what Rust does. Like for example, data race thingies, right? It can be avoided by Rust. It's like even in unsafe code, you can avoid data races with Rust, which probably not possible in other languages, right? So those issues will go away, and these annoying ones like the what is it called, the array out of bound access and these kind of things, they probably will go away, because I think most of these issues also come from someone not realizing. Because if you look at some of the issues in Linux for in the C code, right, some of them are not because they were doing something extremely complex and they had no other way. Some of them were just because they didn't realize that it was happening, like a buffer overflow was happening or something like that. And Rust will avoid those kind of issues. So Rust will at least avoid all those issues which is accidentally happening. And you would only have to look at unsafe blocks, right? For example, I was talking to someone else who is in a security team who audits code for vulnerabilities and stuff like that. And for them, they were talking about like there was a presentation about Rust for them and how they would approach Rust, software written in Rust, and the guidance or the gist of Rust for them was, if it is Rust code block, you only have to look at unsafe code blocks. You don't have to audit the entire thing. Like you can be quite sure that the other part you are not going to find these issues. Only look at so search for unsafe code blocks. Only look audit those for these kind of issues. So at least it makes it easy to reason about stuff, right? Like if you are building a complex software, very sensitive software in Rust, and if you're giving it to an audit team to see if everything is fine, you didn't make accidental memory safety issues, it still makes it much more easier to track down, because unsafe code blocks are like auditable, right? So, and there is even Rust, I think a cargo plugin which can go through your entire dependency tree and find all usages of for all instances of unsafe usages. So you can just even go through that, which is much more simpler thing to do than going through the entire dependency tree and all the code to find issues, right? So I would assume, not like if 70% of the CVEs we have are memory safety, I don't think switching all those software to Rust will magically remove 70% of them, but I'm expecting at least 30 to 40% of them to go away. The remaining would be it's still a considerable reduction, right? So it's and if you look in terms of man hours, like Okay, this is not like some small numbers, right? So where is it? Yeah, so these are not small numbers. Look at these. These are the most used softwares like Linux, Windows, Mac OS, Google Chrome. These are like most used softwares, and 70% of at least 70% of the issues there are memory safety issues. So imagine the amount of hours people spend on these, like fixing these, like handling these CVEs and all these things. Like at least if we can get rid of half of that, like if we can save half of that, it's still a considerable investment, won't you say?
Absolutely. Makes absolute sense. Absolutely. We have some additional questions still here. Stefan, do we have another 2 or 3 minutes? What do you think?
So I guess another question by Daniel. I guess this is something that we can all answer together. So Daniel reminds us of the popularity of C#. I was there when .NET came out in Visual Studio.NET, and there was a fantastic what you see is what you get editor to develop UIs. How's the state of WYSIWYG in Rust? Not there, I guess.
Not there. No, not there
so
yet. Yeah, we are not there yet.
And Raviraj, I hope I pronounced it correctly, likes Rust very much, gives a lot of satisfaction, sees positive news on Rust, but there are not that much openings for Rust jobs in the market. What do you say about that?
Yeah, I think that situation is slowly changing, because one problem is also most of the people using Rust today are either the big companies like Microsoft AWS or the crypto industry. So I know a lot of job openings in the crypto industry because I keep getting these from LinkedIn since they see Rust in my profile. So in other areas, it is still dominated by other language. Like for example, enterprises are still dominated by Java, C#, and these kind of languages. And like data science is still dominated by Python and those stuff. And of course, we have JavaScript on the other front end space. So there hasn't been, like, except for system programming, there hasn't been an area where Rust is like the immediate go-to and you jump in. It will take some time. So given the way that Rust has become popular, I would say it became popular quite fast compared to many other languages, and it has that love from the community, right, which no other languages has. So with that and with more adoption, which is happening, a lot more adoption is happening. Even smaller companies, I personally know some smaller companies which started using Rust because they clearly see the benefit of Rust, especially if they have a use case which is performance oriented, and if they don't have a lot of, and nobody wants to start something in C++ unless they have a team which is already C++ team, right? Because learning Rust is still far more easier than learning C++, and writing good code in C++ is not an easy thing to do. So nobody in their right mind will just like build a new team and start something in that. They will rather go to Rust, and Rust is comparatively easier to learn. So I know personally, I know some smaller companies where they just started doing something small in Rust to see how it goes, so that the team gets familiar with it, so that with the idea that they will switch stuff later. Like a lot of other companies, Discord, I think they switched their some of their backends to Rust, and they even wrote about that, why they did from Go. They switched from Go to Rust. A lot of other companies are doing like Go to Rust. I think you won't see a lot of Java, C# to Rust kind of things, because those are the use cases where Rust is still not mature yet. I mean, web development is not a strong suit of Rust yet. We don't have that ecosystem. We don't even have a really good ORM kind of thing in Rust for databases. Like we have something, but it is not as good as Hibernate or those kind of things. So those kind of enterprises will take time because the ecosystem has to mature. The only thing that is holding back Rust for jobs or the adaptability, in my opinion, is the ecosystem, which will take some time to establish and grow. But once that ecosystem is there, I think it will be inevitable that people will, at least newer projects, they will start considering Rust, because of course there is a lot of advantages, right? Even for like web development, where you traditionally don't care too much about the safety and performance aspects as much as you would do in like a C++ project, right? If you can get those for free, nobody would say no, right? And if the cost and of course Rust as a language, I think, is only becoming simpler with each version. Some of the learning difficulties are being reduced, right? The lifetime things are becoming simpler, and I read that the team is trying to make it even more simpler, so that you only have to use these advanced things in rare situations, not always, right? So as it evolves and becomes a much more approachable in terms of learnability language, and as the ecosystem improves, I think it is inevitable to see Rust as like a huge platform. I would say either bigger than Go, or at least at the level of Go that is today. Go has a huge adoption in terms of job. I don't know the right term for that, but in terms of career options, or these kind of things. So I think Rust will be there in few years at least.
I can see that too. Absolutely.
Absolutely. Super interesting thoughts. And the things that you just discussed and your thoughts about that, it's on the top of the minds of many of the Rust developers, because they want to do what they are passionate about, and they want to earn money with it, and they want to earn a living with it. And therefore, what you said about the ecosystem that has to become more mature is very, very true. Deepu, can we invite you to our Discord server? If you want, you can maybe join.
Yeah, sure.
And maybe for those questions where we didn't find the time now, please ask them on Discord. I see that with just a few additional questions are coming up, but I also see that Nick is already waiting. So Deepu, if you want, we would invite you to our Discord server.
Definitely, yeah.
Stefan,
one more thing.
I can also answer these in YouTube, right?
Yeah, sure.
You can.
Yeah, I can. Yeah.
But one more thing, folks, please put out your clap emoji and give a round of virtual applause on YouTube for Deepu. Thank you very much for being with us.
Thank you.
Thank you so much, Deepu. Thank you. Thank you for being with us, and we were glad to have you.
Thanks for having me. It was really nice.
So, shall we invite our next guest on stage?
Absolutely, we shall. We should.
Hey.
Hello.
Hi, Nick.
Hi, Nick. How are you?
Hi. How y'all doing?
Doing good.
We are fine. Thank you. Where are you broadcasting from? It's always my first question.
I am in London, England.
Nice. So we are a pretty international group here today.
Usually it'd be more international. Like I usually reside in New Zealand. But for a year or so I'm in London. So I'm a little bit closer.
Did you know that in the past we already had one New Zealand edition of the Rust Meetup Blitz? Stefan did that. He spent the whole
with
night
JT and Tim McNamara. They were guests at Rust Linz, and it was very late night for us, very early morning for them. But it was a fun show. It was very enjoyable. And Nick, did I introduce you correctly that you basically did everything in Rust a couple of years ago?
I wouldn't say everything. I've touched a few kind of areas, but not quite everything. But yeah, I was on the core team for a while, language team, compiler team, led the DevTools effort, worked on IDE support, Rust format, cargo, a few other bits and pieces.
That's quite an extensive list already. Wow. Alrighty. So what are we going to hear today?
So today, well, let me see if I can share my slides. This is the part of this software I didn't experiment with.
So if you're not on Mac, you should be good, because Mac usually requires you to restart if you never did that before.
I am on Mac, but hopefully it won't ask me to restart. So let's allow Google Chrome. Oh no, it does make me restart. It makes me restart. So sorry, I will be back in a minute.
Don't worry.
Absolutely no problem. Don't worry. Don't worry. So Nick will be back. If you are just entering now, waiting for the talk of Nick, so please be patient for 1 or 2 minutes. Nick has to quickly restart the laptop in order to allow.
No, it's just restarting the browser. It's not that bad. So
okay,
it's not that bad. Here he is again.
Very
He's
good.
back again. So it just takes a couple of seconds.
Okay, there we go. Yeah, like usually it's just like the camera and the audio that doesn't work. So I was like, well, that works. We're away. I didn't check the screen sharing thing. Okay, let's try this again now that I've done that.
I just got a new MacBook and I stumbled over it again and again and again. So this happens all the time to me. This is...
That looks
good. I see your screen.
Yeah.
I see your slides. Fantastic.
Okay. So, okay, now I can only see slides, but is this looking good?
Fantastic.
Okay, great. So, so what I'm going to talk about is the portability and interoperability initiative of the Async Working Group. So yeah, I don't know. Should I plunge into the talk?
Absolutely. The stage is yours. We are looking forward to the talk.
Okay, great. Thank you very much for the intro. Okay, yeah. So, well, let's start. What is the Async Working Group? So, Async Rust is in this kind of interesting place in that you can do async programming today, very much so. Like the key kind of async and await keywords are implemented, stable. There's some great libraries, but it's not exactly like a great programming experience. It's extremely rough around the edges. There's a lot of kind of like really key functionality that's missing. And so the Async Working Group was formed to fix that. And it cuts across kind of language and libraries and tooling. So it's a real kind of like cross-team effort. And it's doing a lot of exciting work. And today I'm just going to talk about the portability and interoperability initiative, but there are other initiatives looking at things like async functions everywhere. So letting you have async methods and traits or async closures. Or initiatives looking at improving debugging async code and so forth. So it's quite a wide-ranging initiative with a whole bunch of folk working on it. But like I want to kind of like step back a little bit because I want to kind of like make this talk open for people who aren't like really heavily into async programming already. And I also want to, if you are really heavily into async programming already, I want you to kind of like share the mindset that presumably you once had when you discovered async programming in Rust and what somebody new to that today would feel like. So async programming in Rust, I'm going to go through an example, and the example is reading a file. So I'm going to start like, let's just ignore all the async stuff. This is what if we were writing regular synchronous Rust, this is what it would look like. So this is it's just a short function for reading a file. It takes the path of the file as an argument, and it returns the contents of that file or an error. So the first thing we do on the first line, we open the file. Okay, good. Next, we create a string that we're going to read the contents into, and then we call this function read to string, which reads the context of the file into the string buffer. Then, if there was no error, we return that string. Easy peasy. And then calling this function, which we do on the last line in the example, it's so trivial that it's not really even worth me explaining. You just call it. So there's a couple of things that I want to point out. The first is that read to string is not a function on file. It's a function on the read trait, which is an abstraction over any resource you can read from. That's going to be important later, but I just wanted to point that out now. What's actually interesting to our kind of motivation here is that when we're doing this I/O, when we're opening the file or when we're reading from the file, we're actually asking the operating system to do that. And it's going to take quite a long time to do it. I mean, not like really a long time, like a fraction of a second, but like a long time in computer terms, right? And whilst that's happening, the user process, or at least this thread, is just sat there doing nothing. It's literally just waiting for the operating system to complete, and that's just a waste of time. And so that's often the case with I/O. And so asynchronous Rust is basically trying to answer the question, like, what if we could actually use that time productively rather than just sitting waiting, and do that without having to use kind of like full operating system threads for various reasons that it's not worth getting into right now. Okay, so if we wanted to do it asynchronously, first thing we need to do is you need to use the async keyword to say this is an async function. And one effect that has is that when we call the function, it's not quite as simple as before. Actually, calling the function now won't actually do anything. We have to await the results of that function. And this is basically saying, well, this is a function that potentially could take a long time to execute. So let's give the runtime an opportunity to do something else while we're waiting. This is the whole point that I just talked about async Rust giving you an opportunity to do other things while you're waiting. The other thing that the async keyword lets you do, this is an async function, and that means that within this function, we can await other async functions. So when we had this file open to open the file, and when we had this read to string to read from the file, these two IO functions, now we want to await the results. And again, this is signaling to the runtime. These are asynchronous functions. Here's an opportunity to get some other work done while we're waiting for the operating system to finish off doing what we asked of it. Wait, did that? Sorry. So there's a couple of problems though. So far so good, right? You think you're going to do asynchronous programming, you've just sprinkled around a few more keywords, and hopefully things have got more performant, right? We're going to be able to do stuff while we're waiting, which is great. But there's a couple of problems. First of all, these two functions, like file open in the standard library and read to string on the read trait from the standard library, they're not actually asynchronous functions. So we can't wait for them. And in fact, there are no asynchronous functions like this in the standard library. So somewhere we've got to find like functionality that does what we were doing before, but asynchronously. The second problem with this is actually calling this function at all. So I said we had to await calling this function, but I also said that you can only call await inside an async function. Now you can call inside an async block as well, but that's a detail. The fact is that you have this chicken and egg situation in that if you actually try and call this function from main, the compiler is going to complain at you. It's going to give you the error that's on the slide. And we have to find some way to get out of this kind of chicken and egg thing and actually have a way to call async functions. So that's kind of, these are two kind of big problems, and hopefully you'll see in a few slides' time why that's kind of what to do with the interoperability and portability stuff. But let's try and solve these problems. Let's imagine that we're just starting to do asynchronous Rust. Well, kind of, this is a sucky situation, actually. The compiler error here is correct, but it's not really, it doesn't actually help us solve the problem. But let's just imagine that somehow you know that you need a runtime. Like I've said the word runtime a few times, and so maybe you know that you need to kind of somehow you know that you need to go looking for a runtime. Well, let's go to the docs. Great place to start when you're learning is to go to the documentation. Here's kind of the official, or as official as it gets, documentation for async programming. This is the async book on the Rustlang website. Okay, async runtime. So this looks promising. Async runtimes are libraries used for executing async applications. Well, that sounds like what we want to do here, right? And so it continues. Runtimes usually bundle together a reactor with one or more executors. I don't know what those words mean, but let's carry on. Reactors provide subscription mechanisms for external events like Async IO. Well, Async IO is promising. We do want to do some IO, inter-process communication, and timers. In async runtime, subscribers are typically, and it carries on, and frankly, it's just kind of word salad, and it's not really helping me. But let's press on. The future's great. Well, if you've just started writing some like async code, like we've talked about async functions, we've talked about async IO. I haven't actually mentioned futures at all. Now, if you're kind of like deep in the kind of like Rust ecosystem, you probably know that under the hood, async functions are implemented as futures. But if you're new, there's no reason you should know that. So when I'm role playing here, I have no idea why we're talking about futures. But anyway, let's read it and find out. The futures crate contains traits and functions useful for writing async code. Well, actually, that sounds like what we want. Okay, let's keep going. This includes the stream sync, async read, and async write traits. Well, we had before the read trait, and we wanted an async version of it, so maybe async read is good. Okay, let's keep going. Futures has its own executor, but not its own reactor. Still don't really know what this means. So it does not support execution of async IO or timer futures. That doesn't sound great. For this reason, it's not considered a full runtime. Okay, well, let's keep reading. Popular async runtimes. There is no asynchronous runtime in the standard library. And none are officially recommended. The following crates provide popular runtimes. And then we've got a few crates here, one of which is a popular async ecosystem with HTTP, gRPC, and tracing. I actually want to read a file, but maybe that'll work. Who knows? The next one's a crate that provides asynchronous counterparts to standard library components. Well, that sounded like half the problem I had, but didn't it just say that futures would do that, but it wouldn't run my code? The next runtime is a small simplified async runtime. Well, I'm not sure whether I want a small and simplified one or a popular one. Do I actually want an async trait? I definitely don't want a Unix stream. And the final one is an executor for use in the future OS. And I don't even know what that is. So this is a really sucky situation. At this point, if I were kind of learning, I would want to stop. And I don't want you to think that I'm just kind of picking on the documentation here. The problem is the ecosystem, right? The documentation is an accurate reflection of reality, unfortunately. So at this point, I wouldn't really blame you if you just give up and decide to learn Go, because if you wanted to do this in Go, you just add the Go keyword and it's all async now. So that's kind of what we're up against and where we're at. If I've not convinced you to go and learn Go instead, if you're still with me, then I'm going to try and kind of like talk about how we might try and fix this in Rust. But first of all, like you might be thinking, well, like this sounds horrible. Why do we have multiple runtimes anyway? And this isn't just a mistake, or I don't think it's a mistake at all, to be clear. In Rust, you're using Rust because you want precise control of the hardware. You're using Rust because you want to get like absolutely optimal performance out of your code. And we can write async code in lots of places. So if you're writing asynchronous code that is executing on like a tiny embedded processor, that's a really different context from writing asynchronous code that's executing on like a beefy rack server in a data center, like powering some like big cloud system. Likewise, if you're implementing like the file system layer of a database, that's a very different kind of context from implementing like a network load balancer. And so these different contexts have wildly different constraints. And that means that you might want different runtimes. And to really optimize like your code, which is why you're using Rust in the first place, right? Then you might need not just like tweaks to the parameters of these runtimes, but actually like completely different architectures of these runtimes. It's not uncommon for people to write their own runtimes just to get the kind of like performance and other kind of characteristics that they need for their code. Kind of the problem with runtimes is that out of necessity, because there's been no support in the standard library for async programming, they've kind of grown beyond just kind of scheduling, executing your async functions. They've had to have their own like traits for IO, their own implementations of IO, utilities like timers, timeouts, concurrency primitives like channels, mutexes, fences, barriers, whatever. All kinds of utilities, from like low-level things like pinning to higher-level things like combining futures and so on. And the problem with this is that when you go to choose a runtime, you actually have to commit to like a whole ecosystem. And you can't operate with code outside that ecosystem that's using a different runtime. And that's a really like sucky position for the Rust community, for the Rust ecosystem to be in. And that's where the portability and interoperability initiative comes in. So my kind of like one sentence goal for portability and interoperability is that we want to support many runtimes. There's like really strong motivation for having different runtimes, but we want just one async ecosystem, right? We want you to be like, just because you choose such and such a runtime or you decide to write your own runtime, you are still able to use all these libraries that are out there in the async ecosystem. You're not limited to just those that have made that same choice that you have. The corollary to this is that it should be easier to switch runtime. If you start off using a general purpose one, but it turns out after a few months of coding on your project that you need something a little bit more specialized, then you should be able to make that switch relatively easily. And finally, like as I kind of like hinted in the motivation, well, probably more than hinted, we want to make it easy to start asynchronous programming. We want to remove a whole bunch of that friction that comes from having like multiple runtimes in the async ecosystem. To get a bit more concrete, the things that we want to do as part of the portability and interoperability initiative is we want to move a whole bunch of stuff into the standard library. So things like traits for I/O, utility functionality that can be shared across runtimes, that kind of thing. So there's kind of like standard issue stuff. We'd like some kind of abstraction over this concept of an executor to make it easier to change executors, although there's a lot of work to be done there. I don't know exactly what that abstraction will look like. Maybe we'll want to have some executor in the standard library. And we definitely don't want to have any kind of, best executor or default executor or try and replace any kind of existing runtime. What we want to provide is the kind of minimum necessary executor for somebody to be able to start async programming, so they can learn how to do it, so they can kind of like start a project before they have to kind of have all this like deep knowledge that about their project or whatever to choose the best runtime. And there's also kind of like a bunch of kind of paper cuts that we want to get rid of in order to kind of just make async programming easier. So like, what does the shiny future of async programming in Rust look like if we manage to achieve our goals? So let's go back to the example that I started with and see what it would look like. Well, it actually looks pretty much like what we thought it ought to look like. And that's kind of the good thing. But what's interesting is how that's possible. So first of all, let's look at the open function. Well, it would be nice if the standard library on file had not just the synchronous open, but an asynchronous open. And they might even be the same name, and we know which one to call based on the context. So here we're calling await. It's got to be the async function. Now, read to string, that's a function that's part of a trait. And so we should have like an async equivalent of the read trait that's in the standard library. And we can import that pretty easily, just like is shown on the first line in this example. Finally, to call this function, we should just be able to stick async in front of fun main in the same way that we can put result as the return type for main. And the compiler will just figure everything else out for us and it'll just work. Okay, so that's kind of what we want a simple case of async programming to look like in our shiny future. Okay, so for the remainder of this talk, I want to kind of like change the pace a little bit and dive kind of deep into the work I've been doing most recently as part of this initiative. And I want to talk about the Async IO traits and what they might look like. So the IO traits are in the standard library at the moment. Read, write, there's buff, read, and seek. And we want kind of like asynchronous versions of these. And I'm just going to talk about read to kind of try and illustrate some of the issues with async traits and what the eventual design might look like. Some of the same things apply for kind of for write and seek and so forth. But limited amount of time. So this is a vast simplification of the current read trait in the standard library, the current synchronous version. So there's just a function read. The trait abstracts over kind of a resource that can be read. And so there's a function read. You pass it a mutable slice of bytes, and it will read into that slice, and it will return you the number of bytes returned. So async read trait, maybe it'll look like this. The only thing that's changed is we've got the async keyword in front of the read method. And now we can await this, and we can kind of get on with something else whilst the operating system or whatever is doing the read. You can't do this right now. We need async methods in traits, but like I said earlier, this is something that the async working group is looking at, and hopefully will be implemented soon. And so then this will just work. And I think this is a really great starting point. It matches very closely the synchronous trait, and so it should be very easy to transfer your knowledge and experience from synchronous programming to asynchronous programming. But it's also only a starting point. And to kind of like explain why, I have to kind of get a bit more into the details of how asynchronous IO can work. So I just want to start going back with sync. So here's how a read call works in kind of the synchronous universe. So the user process, probably via a library, initiates a read to the operating system. The operating system actually reads from the resource. This could take some time. And when that read is done, the operating system returns that read data back to the user process, and the library presumably will pass it to the actual user code. And like I said before, the downside of this is that while the operating system is doing all this reading, the user process is just sat there twiddling its thumbs with nothing better to do. So the async equivalent of this, there's actually like a couple of ways that async IO can work. Well, more than a couple. There's a couple that we're really interested in. There's the readiness model, and this is what epoll on Linux uses. And there's the completion model, and this is used by IOCP on Windows and IOUring on Linux. So I'm going to go over how both of these two models of async IO work, and how that kind of affects the design of an async read trait in Rust. So let's start with readiness. So again, the user process initiates the read, but this time the operating system immediately returns. And that gives the user the user process some opportunity to get on with something else, right? So that's getting us the async benefit that we wanted. Meanwhile, the operating system is doing the read from its resource in exactly the same way as before. And when that read is done, once the operating system has read that data into its internal buffers, it's going to tell the user process somehow that it's ready, that we're done. And at that point, the user process can read the data out from the operating system extremely quickly. Right? So this is the async call. The nice thing about this is that the user process doesn't need to provide a buffer for it to read the data into until that data is ready to read. So that means if it's allocating, can allocate that buffer like at the last minute, just in time, and then pass the buffer to the operating system and to fill up. It doesn't need to pass the buffer when it's initiating the read. And this can be really important. So consider if this is like a web server or something similar. Then when the operating system is reading from the resource, it's not necessarily just reading the bytes off a disk. It could be waiting for those bytes to arrive from a remote host. And if that remote host is waiting for a user somewhere to like type into a web browser or something, you could be waiting a really long time for this IO to complete. And of course, it's a web server. You're not dealing with just one client. You're potentially dealing with many, many clients, each of which is waiting on one of these reads. And because you don't know how many bytes you're going to get back, this buffer has to be quite big. So you've got many quite large buffers that have to be held for potentially quite a long time, and that would be a huge waste of memory. So being able to kind of like have this memory kind of like on a kind of just-in-time basis is a really big advantage for the readiness model. Completion is the completion model for Async IO is a bit different. Again, we initialize the IO with a read. The operating system returns immediately. The user process can get on with some work whilst the operating system actually does the read. But this time, the operating system tells the user process not when it's ready to read, but then when the read is completed. And the way this works is the user passes a buffer to the operating system, or a reference to a buffer to the operating system when it initiates the IO, and the operating system hangs on to that, writes directly into that, and then notifies the user when the buffer is full. Okay. Now, you obviously lose out on the advantage of readiness that I was just talking about having this just-in-time allocation of buffers. But what you get instead is that the operating system can read bytes directly from the resource into the user's buffer, and so this can end to end. You only have like one read into a buffer, so it's a zero copy process, and that can be really efficient. So if you're doing disk IO, for example, then completion has a whole bunch of advantages in terms of efficiency over readiness. All right, so that's a lightning quick explanation of how Async IO works. Let's see how that relates to the async read trait. Well, before I said we could just have like an async read method, but unfortunately that doesn't really work very well for either model. For readiness, because we only have this one function, we have to start that right at the beginning. There's no opportunity to pass the buffer in later, so then do this just-in-time allocation of the buffer. We have to pass it in at the beginning, and so we lose this like big advantage of readiness. To get around this, I'm proposing we have another trait. So as well as just having the asynchronous read trait, we have a trait that is called ready. So now you have two options. If you don't care about this memory usage so much, then you can just use the asynchronous read method. Very ergonomic, does what you'd want, very easy to use. Great. If you need to be writing memory optimal code, then instead you can call the asynchronous ready method. And note that we don't pass a buffer in here, okay? I've elided a few things from the example, but it's just flags basically. And so so your task would wait for the ready method to complete asynchronously, and when it returns, it says, "Hey, I'm ready," and then you can call this non-blocking read function. And notice that this isn't an asynchronous function. This is going to return immediately, and in fact, it promises not even to block like the synchronous read function does. And that's when you pass the buffer in, and so you have this opportunity to do the just-in-time allocation, or to reuse buffers or whatever, because you have this opportunity to get that memory between when ready completes and when you call the non-blocking read function. So let's look again at completion. So in this case, you do pass the buffer in the beginning, but unfortunately, this still doesn't work with the simple async read method, and that's because of cancellation. So if we were to do the simple async read and the runtime were to pass this buffer straight to the operating system, then one aspect of async programming in Rust is that you can always cancel a feature like an async function. And if that were to happen, then the buffer might get deallocated, right? Because as far as the Rust world is concerned, you don't need this buffer anymore. The future was cancelled. But unfortunately, just because the future was cancelled doesn't necessarily mean the read with the operating system was cancelled. The operating system could have already started reading. And if that buffer has been deallocated and the operating system is reading data into essentially just a dangling pointer, And kind of the whole point of Rust is that we don't read data into a dangling pointer. So this is very suboptimal. So the problem here is really one of ownership. So we're passing like a slice of data from the caller of the read function all the way into the operating system. But logically, we actually need to transfer ownership to the operating system, because the operating system has to own the buffer. It has to be the one that's the only one who's able to write into that buffer while it's doing the read. So this actually fits kind of well with the buff read trait. So I said earlier there's the read trait and there's also the buff read trait. And the buff read trait is a version of reading where we read into a buffer that is managed internally, rather than having a buffer that the caller manages. So if you're happy for the runtime to manage your buffers, then using buff read is a really nice fit. Rather than calling like the read from the read trait, you call read on buff read. The runtime takes care of the buffers. If it's cancelled, the buffer isn't deallocated, so you never have this dangling pointer situation. And you just get back a slice of data. So this is great. This fits the completion model really well, and it means that the operating system can still be zero copy. The problem is that we're returning a borrowed slice of data to the caller. And that's okay if the caller is going to immediately consume those bytes. But if the caller wants to store those bytes, then the caller has to copy the bytes. Whereas what we'd like to be able to do is the caller to pass in a reference to the buffer that it owns, which the operating system can write directly in. So it's zero copy both on the user process side and in the operating system. So a possible solution to do that is yet another trait. And owned read is a terrible name for this trait. I haven't figured out a good one yet. But the idea is that it's very much like the read trait, except rather than passing in a borrowed slice, we pass in an owned an abstraction over an owned buffer. So owned read buff is just a trait that you would implement for like a vec of U8 or for your own kind of custom data types, so that you could temporarily transfer ownership into the library and kind of hypothetically the operating system, so that the ownership works out. And this kind of model seems to work really well with the completion system. It's kind of the part of the design that's still the most up in the air, but I'm hopeful that something like this will work well as part of as kind of suite of Async IO traits. Okay, so that's kind of all I've got for this talk. Just to quickly summarize, I kind of gave you some motivation on what async programming is like today and why we need to improve that. I shared kind of the goals of the portability and interoperability initiative, primarily that we support many runtimes within a single async ecosystem, making it easier to switch runtimes and making it easier to start asynchronous programming. And I also got a little bit into the design work that is kind of currently ongoing with the Async IO traits. So that's all I have today. Thanks for attending this talk and for paying attention. If you're interested in this work, the Async working group does all its work in the open, mostly on Zulip. So log on to Zulip, the Rust Zulip, and there's a stream for the Async working group. And you can see all the discussions we have there. And I'm Nick Cameron on Zulip. If you want to follow this work on social media or whatever, I'm Nick R. Cameron on Twitter and NRC on GitHub, or if you prefer email, that's on the slide. And thank you again.
Thank you so much, Nick.
Very much. Wow, I'm amazed. So I wasn't aware that those were the goal of the Async working group, and this looks like a very promising future. pun intended.
Nice pun. Yeah.
A task for a promising future.
Yeah.
Yeah. Double pun.
And I
Okay.
also found it super interesting because, Nick, I don't know if you're aware of, a few weeks ago, Sishan did a talk about runtime agnostic async crates. I think Sishan is also in the audience today. And so it was a perfect fit, I think. Really, really interesting. Thank you very much.
Yeah, great.
We have one very important question at the beginning, and I think that many of the in the audience ask this question for themselves. That is ETA. That sounds great. Can you give us any kind of suggestion? What you think? What is the estimated timeline before the Async IO would be standardized in Rust? Any idea?
So I mean, it's gonna be an ongoing process. It's not like we're gonna one day have nothing and the next day have everything. And kind of it's one of those things where stabilization is probably going to take a long time as well, because having async methods in traits is really important, and that hasn't even been implemented yet. And we'll probably want kind of I don't think there's kind of a lot of the design question there that's kind of there is quite a lot of open design work there, especially to work with trait objects. But at least in the non-trait object space, there's not like a huge amount of design work. But I think it's still a feature that's going to take a little while to kind of stabilize. And of course, we won't be able to stabilize the libraries using that until the language feature stabilizes. But I would be hopeful of at least some of that getting implemented in the next kind of few months. And that would hopefully be enough to get some kind of early prototype for the IO traits, maybe at least kind of like read and write into the standard library pretty soon after that. And then I would imagine that we're going to be kind of ongoing, kind of iteratively, kind of like evolving those traits, adding more traits, and there's like a whole bunch of kind of stuff that we want to see in the standard library that's not just the IO traits as well. So a lot of kind of like adding on to that and stabilization time. So sorry to give a kind of politician's answer and not just say like 6 months or something, but I don't have a good idea about it, like how long this is gonna really take. Like I hope maybe like 4 to 6 months, we'll see something landing in the standard library, but that might be optimistic. I'm not sure. And I should mention as well, like the interesting bit is not so much that these appear in the standard library. The interesting bit is when kind of every existing runtime is using them. And I think that could take a very long time, because each of the runtimes have their own backwards compatibility issues. Tokyo, for example, won't be able to switch to new traits without breaking backwards compatibility, which mean a 2.0, which they've promised not to do for, I think, another 2 or 3 years or something. So like the shiny future where it's kind of easy to migrate across things, that's definitely kind of like years away, unfortunately.
Didn't I get it correctly that the first thing that needs to happen are async traits to move forward in that area?
Yeah, that's right.
Speaking of async traits, so I do a lot with Tokyo and the Tao ecosystem, and if you don't have an async trait, you usually have a trait that returns some kind of future, either a nipple future or a trait object. And if you are going to do complex tasks within one of those traits, you end up pinning a lot of boxes, which can be very confusing and which can lead to lots of pages-long type errors that are very hard to decipher. And I wonder all the time if async traits might help, because the compiler can figure out things on its own, and you wouldn't have to handle futures anymore, but rather actual types.
Yeah, it should help a lot. And I think it helps like in 2 ways. So one is, just like async functions are just intrinsically simpler than futures. And the compiler can give you, because they're simpler, the compiler can give you better error messages. Even just those error messages are easier to reason about, just because like you can see where the function is. You have a good intuition for how functions work, right? Whereas features are all a little bit mysterious. And the second way they help, I think, is just the style of programming. Like today, you have to fairly often have to fall back to using kind of combinators on features, using things like kind of like join and select macros and so forth. But often that's not a very intuitive way to think about the code that's happening. If you've got like async functions everywhere, and by everywhere, I think kind of this is covering things like streams, aka async iterators now, and kind of async closures and async methods and traits and so forth, then you can write your code in a bit more of a kind of procedural style, right? Like you can just write, foo.await, bar.await, rather than kind of like foo and then bar or whatever, and it's just clearer what's going on. And so because you can use this kind of like clearer style way of kind of like expressing yourself, you just don't hit these kind of like situations where you get the kind of like nasty errors, or where you get kind of like these kind of tricky types of combinators and so forth. So yeah, I'm hopeful that it gets better in both ways.
I will be eternally thankful. So we have this saying at work, every time we are going to see one of those big type errors because we returned the wrong future, that we got towered. that's already a word in our company. But yeah, so that's fantastic news. Really looking forward to that one.
Nick, I would have one additional question that would be interesting for you. Do you see any, or how do you see the relationship of your work, the whole thing that is going on in the WebAssembly world? I'm not thinking so much in WebAssembly, the browser. I'm thinking of WebAssembly with WASM time and WebAssembly interface types and things like that. Definitely things like async work, async processing is an issue there too. Do you see any relations here?
I mean, I have to admit, like, I don't follow the WASM work too closely. Like, I mean, I think it's a really kind of like exciting technology, but there's only so many hours in the day, basically. So I'm not like exactly sure on the ins and outs of how these things work. I mean, I think that kind of like there are interesting questions, I think, in general about when you're using kind of like asynchronous Rust for not necessarily just for I/O, but just for kind of like coordination of your programming. And I think that's maybe where there's some overlap.
I was thinking of things like, sorry?
No,
I was
go ahead.
thinking of things like WebAssembly components, where it's an explicit goal to also let programming languages that support WASM exchange components, where you can use, I don't know, a web server written in Rust, use a WebAssembly component written in Go or something like this, and then you definitely have to bridge gaps between Go routines and Rust features and C# tasks and JavaScript promises. And this was the area where I was thinking about what that could mean for the whole async Rust stuff.
Right, I see. Yeah, so I think that like language interop in the async world is like really kind of like interesting, difficult question, right? Like because some systems are relatively close. Like for example, like C++, like some of the proposed kind of like asynchronous programming there is fairly close to kind of like Rust's implementation. But even then, like quite subtle differences around things like when cancellation is allowed and when like whether a feature is kind of guaranteed complete. Like these different kind of quite subtle kind of invariants mean that like essentially you're incompatible, and there's no way to even like treat kind of like a Rust task and a C++ task, whatever the equivalent to a task is in their systems, like the same. So I think that's kind of a really difficult question. And when you get into kind of things like Go, where you have whole different models of asynchronous, like a Go routine is kind of like a green thread rather than kind of like the stackless coroutine model, which Rust and C++ use. Like they're really different, and I'm not sure like how much you can kind of like expect to get a lot of compatibility there. I think kind of like it's interesting, like, so you have this concept of the reactor in an async runtime, and like this is basically your event loop, and it's just kind of like pumping kind of like IO events and out, and kind of like making sure each kind of async task gets scheduled. And like I think kind of like with WASM especially, there's like, well, can we use the JavaScript event loop like as the reactor somehow? And like being able to do something like that is really interesting. Like it's not that you kind of like tie together kind of like Rust tasks and JavaScript tasks or threads, whatever you want to call them, but like you at least get kind of like some kind of like integration, and so you can kind of, I don't know, like respect some of the invariants on kind of like the from the JavaScript world. This happens on this thread or this thread on things like that. So there's a lot of really interesting, difficult questions there, but I don't really kind of like know the details. I can't really talk to it in any kind of depth.
Super interesting thoughts. Thank you very much.
Ready.
Stefan, I think we are through with the questions, right?
I don't have any more questions. I'm just really, really happy on the development stuff.
Yeah.
So honestly, this is going to be a lot of fun. Thank you so much.
I hope it will. I really hope it will.
Absolutely. And I think this statement summarizes it very nice. Thank you very much for the interesting talk. We will definitely have to rewatch the session to absorb all the details. It was an excellent talk. Thank you very much for being with us. And yeah, we hope to have you with us anytime in the future. So whenever you have something interesting to tell, we are always here for you.
Great.
I especially like the beginning where you were granting all the options going through the documentation. That was hitting close to home.
Yeah, I feel a lot of people will have been through this kind of experience.
Very nice. We also want to invite you, if you want, you can join our Discord server and maybe hang around a bit whenever you want. And with that, could you also share your slides with us? That would be super interesting,
sure.
if you are happy to do that.
Yeah, sure.
Very good. Thank you very much.
And again, for our folks in the audience, please put your clap emojis, hands together, and give a round of applause for Nick for this fantastic talk.
Thank you so much, Nick. Have a nice evening. Thank you for being with us.
Thanks. Good night.
Thank you. Stefan, I think we are through, and it was really interesting 2 talks, weren't they?
Absolutely. I enjoyed all of them a lot. This was a fantastic session today.
Yeah, fully appreciate that. And it kind of comes nicely together, doesn't it? We had talks from the Crosslet team in the past, and now today we had a really nice summary about libraries in the Kubernetes space for Rust developers, and we had the talk of Zishan, and now the talk of Nick together. Will be very, very interesting to see how these things work together in the future.
Yeah, cool. Yeah, so I like it that we get, especially at Rust Linz, that we get some topics that are manifesting themselves that we circle around. So it helps getting a good overview of what's happening, and this is something that I really enjoy.
Yeah, and we have an announcement. We haven't published it on the web. You will be the first to hear it. The next meetup will be, if everything goes okay, will be on the 26th of May, and we will have another topic which is very close to what we heard today about Kubernetes, because we will likely have somebody from Fermion telling us a little bit what they do in the WebAssembly space, and tell us a little bit about platforms like Spin and Waji and things like that. We already covered that a little bit, Stefan, but they are going all in on this topic, and it will be super interesting. And if everything goes very right. We'll have a second talk about macros in Rust, and that will be something very new. We have never talked about the possibility of building what we can do with macros, DSLs in Rust, and I'm looking forward to this talk. So if you want to already save the date, it will be the 26th of May. As soon as we have finished everything, we will definitely publish it on the website.
Cool. By the way, Sishan asks when the next face-to-face meetup will be, and yeah, we are thinking about it. Let's put it like that. So
yep. we are definitely thinking about that, because today was the 21st Rust Linz meetup. So our second birthday is just a few months away. We are already having some chats with some great speakers who might do some talks there. And we are again thinking of an in-person meetup, maybe around our Rust Linz meetup birthday. That would be really awesome. So somewhere in summer, hopefully.
That would be cool, yeah.
Yeah, great. So thank you, Stefan. It was a blast. It was great. I wish you a very nice evening. Wish everybody a nice evening. And I think with that, we should call it a night and see you in May.
Alrighty. See you. Bye-bye.
Great. Bye.